think this is really an exciting time as we look at continued evolution of both scaling in terms of feature sizes, as well as what we're doing in terms of trying to put together new 3D methodologies where we can use stacked dies and through silicon vias to achieve new densities. And I think in both cases there's some key technologies need to come from the EDA side of things. One, we just did an announcement about 2 months ago now for a product called Caliber Real-Time. What's exciting about this is it takes the sign-off physical verification tool and brings it into the design environment so that the custom designer, as he's laying down his custom design, immediately gets feedback on what rules are being violated and where he needs to move things to make that work. Particularly critical when we're looking at 28 nanometer, where some of the rules on base layers just become almost incomprehensible without a technology like this. We're also bringing out new technology and test around areas of what we call diagnostics and yield analysis, so that we can take the fail log information off of the design and use that to understand what type of systematic defects are happening in the fab, so that we can manage yield up in a much more rapid fashion than before. I think those have been two of the more significant announcements. Obviously a lot of other technology in place as well to handle the challenges we see in both verification and test. I think there's been another constant to go along with Moore's Law, which is everyone has been consistently convinced that we're done scaling in about 2 nodes for about the last 10 nodes. I remember when I first came out of school, it was clear everyone knew you could not go sub-micron in terms of design rules, yet here we are. We see a clear path using existing lithography equipment to take it down to a 10 or 11 nanometer node. And then depending upon how we handle the trade-off between restrictive design rules, multi-patterning approaches, and potentially the introduction of EUV as a viable patterning technology, that it's fairly clear how to get to a 7 nanometer node after that as well. At that point we may have to look at a different transistor structure, but that's happened in the past as well. So certainly for the next 6 to 8 years we see scaling continuing as it has been, and after that things may get a little bit more interesting. I think it's very much a bifurcated answer. If you look, double patterning is fundamentally a necessity if we're going to continue scaling to where you take half pitches below 80 nanometers. If you have a single pattern mask with current lithography equipment, 80 nanometers is about the limit in terms of half pitch. And for the 20 nanometer node, there are a number of layers we're going to want to take that to 64. Now, those layers tend to be at the transistor and metal 1, perhaps metal 2 layer. What that means is that the primary people that are going to have to really worry about that are going to be the custom designers, standard cell designers, because they're the ones that are going to have to be actually directly laying things out and watching how it works in terms of patterning. And that's why we've been working with the foundries now for a couple of years on how do we put in place not just rules that tell you when you're wrong, but can also give you guidance on how you fix your problem. For the routing layers, even if you do routing on one of the double patterning layers, the techniques there are fairly well understood. You need to be able to handle placement in an intelligent way so that a single cell which does not have a coloring conflict doesn't go up against another cell and create one. And so there will be some hints and rules involved with the library cells themselves, so then the cells can either be flipped, displaced by one set, so that you can get a color clean compendium of all these standard cells. On the router, it's going to be much more about preferred routing direction, keeping jogs out of the system, and making the jogs as sparse as possible when they do occur. By doing those two things, place and route should end up being relatively seamless to the designer, mostly because of the work being done by the EDA companies to put that into the tools. You know, I think that's a question that has a different answer at different times. Certainly we see for the next 3 years, because of our optimism on scaling, that if you're looking to put together a large, monolithic, homogeneous set of digital logic, you'll want to continue on the scaling path. That's the cleanest way to get that level of integration in a cost-effective way. But what becomes very interesting from the coming 3D technology, specifically around through silicon vias and silicon interposers, is the ability to put a system-on-interposer approach with far better power and performance characteristics than you can get out of a system-in-package approach that'll let you do integration of things like memory to processor, sensor to processor, RF and analog into processing elements that will be very attractive for putting together systems rather than on chip, systems on silicon interposer. That'll also give us the time to get a significant amount of learning done on the TSV itself, the through silicon via. And where we think that turns around is when we get to the point where we understand how the through silicon via will affect active circuit area, how dense an interconnect structure we can get in each one of those dies. That's when doing the aspect of maybe taking multiple logic chips stacked together could start to become interesting, and perhaps at that 8 nanometer, 7 nanometer node may end up being an interesting and viable alternative to a scaled technology down to 5 nanometers. Yeah, that was an interesting question, because if you looked at what people were talking about this as much as 6-9 months ago, everyone was talking about how revolutionary this would be. And that was mostly because people were thinking about that homogeneous logic partitioned among multiple dies. And that indeed will be a harder problem. Everything about placement, everything about pathfinding needs to now understand this difference between when you're routing within the die versus popping up through the stack. But as I was saying before, that looks to us to be something people are going to be really doing more of a dominant mode maybe 5 years from now. The approach where you use the through silicon via and a silicon interposer to then take multiple die and package them in the same part, that gets to be a much more incremental approach. You get an issue in test. You got to be much more careful about your known good die problem. If you get test escapes because of the way you're doing test, you then not only waste that in a package, but every other die you're putting together with it. And in addition, you have to make sure you have an effective test methodology that handles the fact that many of the die within the package don't have a direct connection to the outside world. So how do you connect all these things together? How do you reliably test memory? And that's where some of the work we've been doing over the last few years on SoC test really comes into play and is very effective. Things like being able to do memory BIS that you put on the digital chip that then tests the memory. Things like I/O BIS, things like hierarchical test with compression to low pin count. All those technologies have been being used by advanced SoC users, directly applying to the 3D space. On things like physical verification, the key then becomes how do you verify now interfaces between multiple dies, given that those dies are in different technologies, likely have a different scaling from physical to database size, have different rule files, and we've been working with both lead users as well as lead foundries on putting together flows that allow us to effectively do that, so that you can make sure that indeed you put the pads you put your pads where you're going to do your micro bump in the right place to land on the through silicon vias in the silicon substrate, and you have a reliable manufacturability as well as the ability to then check on all your interconnect and whether we're forming the circuits that you meant to do. So I think for the way we see it playing out over the next 3 or 4 years, it's an incremental approach that is primarily a solved problem. For 5 years from now, we have some time to work on some of those more novel approaches that we need to put in place. It's really exciting to be able to come over and meet with the companies in Israel. I mean, if you look at the dynamic nature of the startup space here, it's an interesting environment where you have people that have been working together for years, that move from company to company to build up new value. The amount of sales you've recently had of companies to other companies, it's an exciting place in terms of the startup vibrancy. It feels a lot like Silicon Valley did 15 years ago. Whereas Silicon Valley is kind of moving away a little bit from the semiconductor space, Israel's really filling that role. So I love working with people over here, and I love a good argument, so it's a great place to be.